We deserve that for showing up.
Yeah. If you told me that you need help with everything in the homework, bro, I'm just gonna tell you to look at the video from last week. But I will remember your faces. You're gonna get some extra points for showing up today.
Thank you.
So,
You don't get the
No.
I actually, we were just
Yeah.
catching up with.
okay.
I did my.
They were just waiting outside.
I
Take your voice.
have data, but I'm unclear how to draw the lines on the block using that data I solved for. Like I have my block set up.
For this one.
Yes. So like I'm just at the very end where I need to draw the dotted lines like what you did in the notes.
Yes.
And I'm unclear how to do that. Very
Okay,
last step.
let's see. In this case, for number, which problem you say number 2? Number 2, we have a site which is subjected to reverse faulting, right? The maximum horizontal stress is the maximum, the minimum is vertical. So this is going to be very similar to this case over here. Furthermore, let's see, the orientation is east-west. So that one is going to be very similar to this one, but SH max is going, let me read that again. Make sure that I have it right. Yes, SH max is east-west. Therefore, it's going to be exactly the same like this, but rotated 90 degrees. You see that? So in this example, SH max is striking north-south, but in the other one is striking east-west. So the strike of those faults, instead of being now east-west as it is in this example right here, is going to be north-south. And the dip of those faults is going to be 90 minus beta. Okay? Make sense? Yes?
Yeah.
Okay. Any other question about this homework which is due today? I can help you with?
Going over 4, please.
Yes.
So, just to clarify, the direction of your dots for normal faulting will indicate the direction of SH min. And for
Well, I don't like too much to make rules like that, because sometimes those rules, I'm not saying they're going to fail, but I prefer to interpret as soon as I see the points to look at the faults, and after I see the fault, I can tell what's going on.
so then, okay, so my question to you is,
Yeah.
like, how do you determine the direction of stresses after you determine the regime on the steeriness? Because that's the disconnect I have. Because I know that the first one
Okay.
is the reverse faulting and the second one's normal, but I don't know the directions easily.
All right, so the first one is, as you said, reverse, because the dip of those faults is 30 degrees. Those are gently dipping, and those fractures are very similar to this. Actually, it's the same as we were discussing before. These faults are striking north-south, right? And it will be equal to this by rotating 90 degrees. So after you see the faults and you see that that these faults are gently dipping, very likely, if they are gently dipping, those will be reverse faults. If they are steeply dipping like this one of 60 degrees, then it's most likely that these are going to be normal faulting. So in this case, once this is going to be the strike of the faults, right, of the two faults, the two sets of faults, and if this is a strike and I know they have a dip which is more or less 60 degrees, I would tend to think that the most likely scenario for those faults is to be normal faulting with SH mean going in this direction.
Okay.
Make sense?
Yeah, because you're just looking at that picture. and
Yes.
Kind of
Yes, I'm looking at that picture. I'm trying to.
Oh, it's dipping towards SH.
Yeah, I'm trying to take this picture into here,
Exactly.
and in order to do that, probably I'll have to rotate this entire block along the vertical axis 45 degrees clockwise,
Got it.
and you will get what you see in the with the blue dots. Okay. Anything else? Yes.
So you said you know if it's reverse or normal depending on the angle?
Yes.
Okay.
Yes. So most times, gently dipping faults, if they were caused by faulting, those are going to be this type of thrust faults. If they are quite steep but not 90 degrees, very likely those are going to be caused by normal faults if the state of stress is still the same. And last, if the faults are 90 degrees and you see them, they have strikes which differ by an angle of more or less 60 degrees between here and there, then those are going to be strike slip. So I didn't add a strike slip example here, but remember those are points that plot something like this. All right?
In actual project, is it just easier to just have those three categories and just forget about anything in between?
Well, it's easier to think on some extremes or some, ideal scenarios when you get to analyze other faults in reality, because there then you can see to which regime they are closer to. Okay, yes?
Dr. Espinosa, when we determine the azimuth of the strike,
Yes.
do you want us to rigorously follow the convention?
No, I just want you to know the two conventions, but I'm gonna, you can use, if I don't specify which one, you could either use, for example, this one or that one.
Oh, I mean the right-hand rule convention.
For the fault.
Or the azimuth.
So for azimuth is defined as an angle in clockwise directions from the north towards a line.
Right. So
Right.
if we're using the one where it's angled from the north, do you want us to rigorously follow the convention?
For the azimuth, for this one, yes. But you could also express it like that.
Okay.
So,
Either way.
Spinoza, it could be like the angle, or it could be the angle plus 180 degrees. So that's one question. So which one, is that a preference?
There is one solution which is correct.
Only one.
Only one, but that requires to learn something that we didn't go through, which is the orientation of the coordinate system of the fault. So either answer will be fine. I'm not going to ask you to remember which one, but either that angle or that angle plus 180 degrees, that I'll consider that correct. Okay?
No, we don't have to use the convention, but that's because
No, don't worry about that right now. Yeah. Okay. If we don't have any other answers, then we'll go to homework number 7. Okay? It's not too difficult. Just a few more things that we have to work on. And the first problem is a problem about a Mohr circle. So we're gonna solve it together, but I'm gonna give you a few hints about how to get started. So for problem number 7, let me see if I can make this work. Homework number 7, problem number 5. This is what you have. You have a reservoir with these given stresses and pore pressure, and you know in which direction minimum principal stress is going. So the first thing I'm going to ask you here is draw the block diagram with all the stresses in it. Okay? And I'm going to ask you one more thing. After you draw the block diagram, please go ahead and calculate effective principal stresses. And after you do that, before starting to solve the problem, you can here draw the 3D Mohr circle. So draw the three of them, okay? So get started with that. If you have a question, let me know. And as promised, I'll go through the list and add a point to you here.
A grade point?
What? An extra point. I'm going to give you an extra point just for showing up to
Get a
the...
letter grade?
It depends. You know how it's the rule with the extra points. If you are borderline
Yeah.
from the grade, a letter grade to another, probably getting this extra point could help you go over that from say 89.999 to 90. If you didn't have this extra point, you wouldn't have that. Okay. So, all right. So guys, start working on the problem, please, and I'll complete this. Mr. Marwaha, is that you? No? Not here? Okay. Mr. Momin, that's you, right? Okay. Please let me know, or Mohammed know he's here too if you need any help, okay?
Now this is beautiful. I want to help people who come. What? It's not a big deal.
Mr. Jamal. Mr. Jamal is here?
No, he's
No?
I would be very surprised if he
Hamza Jamal? No? Fahim Islam? You're here. Okay. Good. Mr. Mahaini? Not here? No?
They're all seniors, they're not sure.
Okay. Miss Mendes, right there, okay. Mr. Olgin. All right. I think I got it, everyone. Oh no, there's one missing. Okay, so how is that going?
Would it be best to start off with hysteria from 5? Or should you just go straight to the cube?
No, straight to the cube.
Alright, cool.
Yeah. So SH mean. SH max and what is the value of SV? And what is the stress regime here? Looks like strike slip, right? Okay, so remember always to write here what is your coordinate system. And what are the effective principal stresses? Sigma H max, anyone has the value? 40 MPa. Sigma H mean? 20 MPa. And sigma V? 25 MPa. Because we know here that pore pressure is equal to 20 MPa. All right. So I hope you are all up to this point done, and now you have to draw the Mohr circle. Okay. So in the exam, if possible, I'll try to give you a paper with grid lines, so that helps you draw more circles if needed. But this is more or less like this: 40, 20, 10, 30, and 40. And therefore this should be 10, 20. Okay, are you guys there already? Did you? I'll go around and see if you are. Please start drawing your Mohr circles. So I want to do it before you do it. I'm doing it just for you to check if it's the right solution or not.
Yeah, but notice that now this is the problem. It's not about ideal orientation of fault. It's that you have some fault. You have to calculate stress on the fault. Okay. Yeah. Yeah. That's one. Well, but it's said over there, right? It says Shmin acts east-west. The fourth line. Yeah, for every condition, every part in the world you go, Shmin is going to be oriented in some direction. In this particular example, it goes in direction east-west. So that wasn't if I told you that those folds are there, I'm asking you what are the stresses that cause those folds. And that's why you have to figure out the stresses. But this is another problem. I give you the stresses, and I tell you that there are some folds. I'm telling you these are the stresses. There are some folds, we need to calculate the stresses on those folds. Well, asking you to find out the stress. You don't know the stress. No, it's just but you know that those folds were caused by some stress. You need to find out what those stresses are. So this one yeah.
So it goes up to R. So R is equal to sigma H minus sigma H
Yeah. What actually you do because you draw a line here.
Supposed to be a white here.
And you say how close
I feel like just my
it should just go here and
So, but you know, it's a problem in which it's not a problem of ideal orientation. It's a problem in which you have some stresses when you have some faults that were probably created a long time ago before the stresses came to be as they are right now. So even those faults all orientations we need to calculate shear stress and normal stress acting on those faults. So sometimes when we said about the ideal orientation of the fault, that's a particular case.
Like not terrible, but like they kind of shitty. They like take more rotation, like everyone else gets good.
Remember, that example I showed where we have the 3D Mohr circle and there were like thousands of faults, all many types of orientation. From all of those would like to know what yeah. Okay, but you have to go through this. Okay, so just wait a bit, and then we'll continue. Yeah.
So, I just have a couple of conceptual questions for you. So the first question I have is that this is concerning. So whenever you ask for how do you always fracture inside the segment?
Well,
They give us this formula. They see this. The formula is on top of that.
but it's always
Right.
ideal
How do you make this one?
Sigma 1, Sigma 3.
I mean, that's what you need to do. That's why you need to do this.
I mean, not exactly as hard. There's a lot of practice. I don't mind being
Like maintaining a
Wait, I'm going to define that. So all the calls are logged. But I don't know how you call
All right, guys. Let's continue with this problem. So, as soon as you know the orientation of stresses, you can calculate effective stresses. Now you put those in the Mohr circle. Always, since these are all principal stresses, remember that in the Mohr circle, those are going to be points here in the x-axis. So we have 20, 25, and 40. Okay? We can make 3 circles out of these 3 points. So the first one is going to be this one, second one, something like that, and the third one is going to be something like this. So now it's where it gets probably a little bit more complicated. We need to understand which circle corresponds to which combination of faces here in the Mohr circle. Okay? Yes?
How did you know how tall?
Here? Well, notice that I made my scale more or less the same in the y-axis as in the x-axis. So since this is a circle, then the radius, if this is the center, the radius should be about that. Probably I should have made it a little bit taller. Okay, so notice that this problem is different to what you had before in 1 to 4. In 1 to 4, you were asked to find ideal orientation of shear fractures or the ideal orientation of stresses based on your shear fractures. In this case, we have a state of stress. It is that. And we have some faults that have been created there. And may or may not be related to the current state of stress. The state of stress changes with time. And you have maybe have some fractures that were created 10 million years ago that do not coincide with the current state of stress. So in nature, not necessarily you're gonna always find the fractures at the orientation in which you expect them to be with the current state of stress. But in this case, this is our current state of stress, and we know that we have these 4 faults that we'd like to investigate if they are close to reactivation or not. So the first one, it's a fault that strikes north-south with a dip of 65 degrees to the east, okay? So can you see the fault here with those geometrical properties? So first of all, strike north-south. So probably it's going to be a line somewhere over there. And the dip is 65 degrees. So it's going to be steeper than 45 degrees, probably something like that. And this is going to be number 1. Okay, tell me, that fault could be thought as a combination of which 2 planes? SV and SH mean. Remember that there is another plane of SH mean here that we can't see, and which is on the hidden face of this block. So that's another plane of SH mean. And therefore, if you want to understand this and see where that plane is a Mohr circle, you're going to have to go from the plane of the maximum stress to the minimum stress. In this case, which one is bigger, SV or SH mean? SV, right? So that plane of SV is this, sigma V. No. Wait. This is sigma H max, right? Sigma H max, sigma V, and sigma H mean. Combination of sigma V and sigma H mean is going to be that small circle. So sigma V, sigma H mean is that circle, and if we want to find where that fault is, we need to go an angle of, in this case the dip was 65 degrees. We need to go 2 times 65 from the center of that circle towards over there. So let me write this over here. This is 2 times 65 degrees. So you can compute the center of this circle and the radius of this circle, and using the same equations that we used before, you can tell me what is the shear and the normal stress at that point.
Can I ask why you chose
Yeah.
that circle? Sorry?
Why I chose the small circle?
Yes.
Because the plane, we say, is a combination of the plane of SV and SH mean. So if I want to solve that, I need to go to the Mohr circle that combines sigma V and sigma H mean. Yes?
To be clear, beta always equals to nib, correct?
No. And let's, so Are we okay with this example? I'm not going to calculate what is tau and sigma m, but you should do that, right? So for that point, or let's call it fault number 1, you have to tell me what is tau and what is sigma n, and what that will depend on the center. Let's call this one C1 and this one R1, and that depends on the values of, let me zoom in, that would depend on the values of sigma h min and sigma b, because we were looking at that plane. Let's do the second one. The second one, it's a fault with strike east-west and a dip of 35 degrees to the north. Let me think about that. And okay, I think now the bait is going to be different. So first of all, let's do the strike. That's the easy part. Fault number 2, strike east-west, and then the dip is 35 degrees to the north. So this is going to be something like this. This is the strike of number 2, and the dip is that, and this angle is 35 degrees, and it's dipping towards the north. Unfortunately, there I cannot draw very well what would be the hidden lines, but I'll try. So it's going to be that plane. Okay? Okay. For this plane, number 2, probably when you do it in your homework, just make another block, so it's going to be easier to look at all of those faults together. That plane is going to be a combination of which faults or which faces in the block? SV and SH max, right? So if this one is a combination of SV and SH max, we need to use a Mohr circle that combines sigma V and sigma H max. So it's going to be this circle, okay? Now, which is higher, SH max or SV in this case? SH max, right? And what is the angle that you need to go from the plane of SH max to the plane of SV to get to that plane? How much? 55 degrees. Can you see that? Where the 55 degrees come from? So 55 degrees is the angle. Let me plot an auxiliary line here that you require to go from the plane of SH max, which is this one, from the plane of the fault, and it's 90 degrees minus 35. So let's take these 55 degrees now to the Mohr circle. 55 degrees times 2, that's going to be 110. So if this is the center of this other circle, 110 is going to be a point somewhere over there. And this is going to be 2 times 55 degrees. And that fault is going to be a point right there. And now you see that in this example, the angle beta is not the dip, but is a complementary angle from the dip in this particular case. Yes?
So just to clear out something.
Yeah.
Can you go back to the circle?
Yeah.
So it's going to be in between, the point would be in some space between the biggest circle and another circle if it's a fault that cuts through all 3 planes, basically, right? Is that how this works?
If you have a fault which does not coincide with any of these direction, it's an oblique plane, it's going to be somewhere in between. Yes.
No, I see what you're saying.
Um,
That's kind of like the first drawing that you usually do, like when a cube is sliced
yeah,
diagonally.
yes, correct. Each circle is a solution for combination of just two planes. And everything in between is when you have an oblique plane. And the third one is very similar, but now notice that you have a strike which is not coinciding with the north or the east. It's some angle, but the dip is 90 degrees. If the dip is 90 degrees, that means that's a vertical plane. If that's a vertical plane, that means that it's aligned with SV, and you should be able to solve it with a 3D Mohr circle. And it's going to be on that bigger Mohr circle. The last one, though, look, it has some strike that does not coincide with the horizontal stresses, and it has a dip which is not either 90 degrees or 0. So you're not going to be able to solve that one with a Mohr circle, and it's going to be a point somewhere in between. So I'll let you solve that, and let me talk a little bit about well, problem number 6. You're not going to solve it. If you want to solve it, I can help you. Mohammed also will be glad to help you if you want to solve that one, but you don't have to. And problem number 7 and number 8, let me skip them for now because they are very similar, and go to problem number 9, which I didn't upload yet on the website, but I uploaded in my notes, and I think it's a very good one. But I have it here, but I will upload it during the week, guys. Don't worry. When you are back from spring break, you will see it. So let's see, files. Okay. This is problem number 9. In problem number 9, you need to understand this geological map. Basically here, where is this, guys? Eagle Ford, right? This is Eagle Ford. San Antonio is right here, Austin somewhere over there, and this is the Eagle Ford play. And what you see here as blue lines are faults, and are mostly normal faults. And what you see as a line is also the strike of the fault. So you may think as all of these lines as planes that are oriented like this. So you have to do two things. Based on what you see in this map, and knowing that these are normal faults, I want you to tell me, what do you think is the orientation of the minimum principal stress in the Eagle Ford basin? Okay? And probably you already have an answer. And once you have it, okay, I want you to verify it. And the way you're going to verify it is going to be by using the Railroad Commission database. And here you have this GIS viewer where you can see location of wellbores. So we're going to use this later on too. So you go here, you see San Antonio, and anyone from San Antonio? Cool? No one? Okay. So I want you to go specifically to this Frio County, but you may check everywhere else, okay? So I'm zooming up in Frio, And at some point, you're going to start to see well bores. There you go. So these are all surveys of the heel of the wellbore and towards the toe of the wellbore where it finishes, right? So here the lateral starts, here it finishes. These are the orientations of horizontal wellbores. So based now in this map, what do you think is the minimum principal stress direction? Knowing also that basically here you want to make fractures which are perpendicular to the wellbore, right? So now let's look at those together. Did these companies in here drill the wellbores apparently in the right orientation? Or does that coincide with what you see from the faults? Well, I want you to answer that, okay? But I guess you already have the answer. And remember that out of solving all the problems, I expect you to be able to solve problems like this one. Okay, last two problems. Number 6 and number 7. Number 7 and number 8. Problem number 7 and number 8 are about solving stresses, knowing what the limits of stress could be. So problem number 7 is mostly a generic problem, and number 8 you need to compute stress at a particular location. But basically what this is telling you is to compare what will be the limits of S1 and S3 for normal faulting and reverse faulting. Let me ask you, which is the easiest stress to calculate or to estimate from all stresses possible in the subsurface? Vertical stress. Always vertical stress is the easiest one. And there is a lot of, it's just a weight of rock on top. Or if you got some water, you add the water, but that's it. There is not a lot of uncertainty in that. So we always know more or less well what SB is. Yes?
Oh, we can't see
We always know very well what SV is. Relatively easy to compute. So if you are in normal faulting regime, SV is going to be S1, right? And what is going to be S3? So if you're in normal faulting and you know the vertical stress, with assuming that the faults are at shear failure, you're going to be able to calculate sigma h mean with this equation. And the opposite, if you are in reverse faulting and you know what is the value of sigma v, you're going to be able to calculate the value of sigma h max, because this is going to be just q times sigma v. Remember that for these two equations, I'm assuming that sigma 1 is equal to q sigma 3. So what this problem is asking you is basically to compute values of S1 and S3 for both normal faulting and reverse faulting, considering that the friction coefficient is 0.6 from 0 to 5 kilometers. But basically this is what you have to do. Basically, if just give me one more sec, guys. If this is SV and This one is your pore pressure. If you are in normal faulting, your SH mean is going to be somewhere over here. If you are in reverse faulting, your sigma H max is going to be 3 times this distance, so somewhere over here. And notice that it's very important over here that later in the second problem, we do not assume a hydrostatic pore pressure anymore, but we assume a case of overpressure. And in that case, this distance gets smaller, and so the difference between the total stresses gets smaller too. But those problems are not very difficult, and we can talk about that when you come back also from spring break. Okay? So enjoy your spring break, and I'll see you in 10 days from now.